Hello, how are we doing? So we're doing Module 3 of Introduction to Network. So it's protocols and models. So it's networking models actually, so how networking works. Okay, so we're going to explain how network protocols enable devices to access local and remote network resources. And so we're going to look at the rules. And so basically rules so that computers need to follow to communicate, protocols, and basically that's how we set out the rules. Suites, and so groups of protocols that work together to get the job done. Standards organizations, and so who's involved in creating these standards. Reference models, and so this is the models it was speaking of, and so it's TCP/IP and the OSI model are just explain exactly how the communication works. And then we'll talk about data encapsulation as well as data access. Okay, so the rules. And so networks can vary in size and complexity. It is not enough to have a connection. Devices must agree on how to communicate. There are three elements to any communication. There will be a sender, a receiver, and the channel which it moves through, so which we often call the media. And so, of course, it's not enough to have a connection. So it's much the same as putting people in the room. If they don't speak the same language, the communication's going to be a problem. And so that's the rules here are, of course, we all speak the same language to be able to communicate. And so protocols are the language. And so all communications are governed by protocols. Protocols are the rules that communications will follow. These rules will vary depending on the protocol. And so basically they're comparing a human conversation with a computer conversation. And so, of course, the message source, the female does seem sensible to me. And so what's the transmitter? Well, it's their voice box. The transmission medium is the air. So, of course, the sound waves travel through the air. And then, of course, the receiver is the man's ears, and then of course the destination is the brain, and so of course they need to translate those sound or noise into a message that they can understand. And so much the same process here. So a message, that could be an email or a web page or whatever it might be. We then need to have something that transmits that. So network interface card on the sending computer, transmission medium, and so Ethernet cable is as good a choice as any. And then receiver, of course, is the NIC or network interface card on the receiving computer, and then the destination is a web browser or an email client or whatever it might be. Okay, so rule establishment. So individuals must use established rules or agreements to govern the conversation. The first message is difficult to read because it's not formatted properly. The second shows the message properly formatted. And so also we've got, I'm assuming that's another language. and so basically, we've got, it's just a little easier to read. All right, so protocols must account for the following requirements: an identified sender and receiver, a common language and grammar, speed and timing of delivery, confirmation or acknowledgement requirements. And so a protocol or a group of protocols must get all of these things done. Okay, so network protocol requirements. So common computer protocols must be in agreement and include the following requirements. So message encoding, and so how do we format messages? How do we do encode ones and zeros on the medium, and all kinds of things like that. So formatting is what goes before what and goes where. How we encapsulate, much like posting a letter, we have an envelope around it with addressing information on it. Well, that's much the same thing as what computer communications do. Message size, message timing, and delivery options are all things that need to be formalized and agreed upon. Okay, so encoding is the process of converting information into another acceptable form for transmission. Decoding reverses this process, and so encoding is the source computer, decoding is the destination computer, basically. And so they're showing that, you know, it's on the source to start with. So I'm assuming it's a picture we're talking about. Maybe it's a video. And so you have a message, you need to encode it, and then you need to transmit it over the transmission cable. Then it needs to be received, decoded, and then it's at the destination. Okay, so when a message is sent, it must use a specific format and structure. Message formats depend on the type of message and the channel that is used to deliver the message. So I did mention envelopes earlier, and so an IP packet is very much like an envelope. We have a destination IP address, which of course is the recipient's address here, and then there's a source IP address, which is the guy who sent the letter, and other information just so they can keep track of one another. And so looking at the size of the IP addresses, I'm assuming these are IPv6 addresses. Okay, so message size, encoding between hosts must be in an appropriate format for the medium. Messages sent across the medium are converted into bits. The bits are encoded into a pattern of light, sound, or electrical impulses. The destination host must decode the signals to interpret the message. I'm not sure why it's called a message size here, but anyway, we're more talking about encoding than anything. But anyway, and so yes, of course, you know, when you're sending a message across copper cable, of course, you need to agree on what kind of electrical signal means a 1 and what kind of electrical signal means a 0. And same with optics with light, and the same with you know, what you do with the frequencies when it comes to wireless or other waveform manipulation. Message timing, so includes the following. So there's flow control and response timeout. And so flow control manages the rate of data transmission and defines how much information can be sent and the speed at which it can be delivered. So it could be, you know, it's probably done in more than one place. So, you know, when we're talking about Ethernet, you know, there's fast Ethernet and there's gigabit Ethernet, and so they have their own sort of rates of transmission, but that's sort of very low level. Of course, higher level, we've got you know, we might have a client that's talking to no one else but this server, but the server it's talking to might be talking to hundreds or thousands of hosts, and so, you know, you might need to slow down transmission to that server if there's lots of hosts communicating at the same time. And so there's several levels of that. So response timeouts, and so manages how long a device waits when it does not hear a reply from the destination. So with most at least reliable communications, when you've received a part of the information and it's arrived without errors, you normally send an acknowledgement back saying, hey, yes, I've received that. Now, if that acknowledgement doesn't come, well, how long do you wait until you think, well, it mustn't have gotten there, so I'm going to have to resend that information again? And so that's basically what we're talking about here. And so, of course, so the different protocols have different ways of managing that, of course. Access method determines when someone can send a message. There may be various rules governing issues like collisions. This is more when more than one device sends traffic at the same time and the messages can be corrupted. Some protocols are proactive and attempt to prevent collisions, while other protocols reactivate and establish a recovery method after the collision occurs. So the proactive one, you could probably talk about wireless a bit. It does do collision avoidance, while Ethernet, at least back in the old days when we had hubs and buses and things, it just used to let collisions happen and then it would recover from them. Probably not the most efficient method, but anyway, we're switching. It's near irrelevant now anyway. Message delivery options. So basically for most protocols, you've got the three major options. So a unicast is one source sending to one destination. A multicast is one source to a group of destinations, but normally not all. And then a broadcast is one source to everyone else. And so that's basically what we're showing here. So one destination, in this case, it's two destinations, and then it's everyone. Now, broadcasts are used in IPv4 networks, but are not an option for IPv6. And so basically there is the option as an anycast, but also IPv6 does a lot more multicasting when it's trying to find information out. Note about the node icon. Now, documents may use the node icon, typically a circle to represent all devices. The figure illustrates the use of a node icon for delivery methods. And so, again, unicast, multicast, and broadcast. And so the green ones are the one, well, the orange or brown is the sender, the green are the receivers. Okay, protocols. So network protocols define a common set of rules. They can be implemented on devices in hardware, software, or a bit of both. And so protocols have their own functions, formats, and rules. And so there are different types of protocols for to get different jobs done. So network communications enable two or more devices to communicate over one or more networks. Network security protocols secure data to provide authentication, data integrity, and data encryption. So we're talking about IPsec there. Routing, of course, is routers talking to one another, exchanging information. And so, of course, that's how routers learn remote networks as destinations. And then service discovery, used for automatic detection of devices or services. Okay, so devices use agreed upon protocols to communicate. Protocols may have one or more functions, I'm assuming that's talking about there. Now, addressing, identify sender and receiver. Reliability provides guaranteed delivery. Flow control ensures data flows at an efficient rate. Sequencing uniquely enables each transmitted segment of data so it can be reassembled at the destination. Error detection determines if data became corrupted during transmission. An application interface is basically how you can get applications to talk to a network. And so it's the interface between the local applications and the network. Okay, so an example here is if we've got a web browser talking to a web server. They, of course, talk using HTTP, Hypertext Transfer Protocol. TCP is the transport layer protocol that actually manages all of that. IP, of course, is the one that identifies the source and destination and gets it from the source to the destination. And Ethernet, of course, is controls a medium that will actually transfer the ones and zeros across. Now, protocol suites. So protocol suite basically means there's more than one protocol that needs to be used to get the job done. And so, if we look at previous slide, of course, we had 4 protocols mentioned there. So that's basically a suite. And so the protocols must be able to work with other protocols. And so a group of interrelated protocols necessary to perform a communication function, a set of rules that work together to help solve a problem. The protocols are viewed in terms of layers. So there's higher layers. And so that's more about the data and who it's going to move to. On the lower data is concerned about actually the lower layers about moving the data and getting it to and from the upper layers. And so when it comes to the most common protocol suite out there, it's TCP/IP, or the Internet Protocol Suite. And so basically here we have this is by no means an exhaustive list of application layer protocols. But pretty much some of the most common ones. HTTP, of course, for web pages. DNS to translate host names into IP addresses. DHCP to give host configuration. And FTP, you can move files. And so these, of course, have different needs of reliability and other such things. And so there's actually a choice of 2 transport layer protocols, be it TCP or UDP. TCP is industrial strength reliability, while UDP is quick and dirty. And then down here on the internet layer, you've got a choice of IPv4 and IPv6 and other protocols there that sort of help get the job done. Then down the very bottom is, of course, the medium itself. And so we're talking about Ethernet as being the most common one. And so TCP/IP is basically the major one most people will use. And so because the internet uses it, basically now pretty much everyone is adapted to using TCP/IP. Now, before the internet became a big thing, many vendors had their own solutions that did roughly the same job as TCP/IP did, but of course they were different, and so they were not compatible with one another. And so, like Novell, if anyone's ever heard of them, maybe the oldest ones amongst us, that was a server solution that was very, very popular back in the 90s and before. And so it had its own protocol suite, which many people used to call IPX SPX. So Internet Packet Exchange and Sequence Packet Exchange is what they stood for. And so roughly the same jobs as what IP and TCP did. NDS is, I suppose, the major thing that they think of. If you've played with Active Directory in the Windows world, well, that was a copy of NDS. And so, of course, basically the network access layer is common amongst all of them typically. Now, Apple, of course, had its own one. Many people used to call it Apple Talk. And then ISO, which is the International Standards Organization, has developed its own protocols as well. So CLNP is Connectionless Network Protocol. That's the equivalent of IP, basically. And so there are transport layer protocols available as well and the like. I've got to admit I haven't done much with ISO. I have done a little bit of CLNP, because if you do ISO's routing protocol, you actually do need to do a tiny bit of that. But yeah, I've done a tiny bit of Apple Talk and Local Talk. And yes, I have done Novell back in the dark ages. But also Microsoft used to have its own protocols as well. So it was called NetBEUI. And so that was different again. And so, yeah, they've all either translated to TCP/IP or fallen by the wayside. There were other vendors that did it as well, things like DECnet, Digital Equipment Corporation, and so on. And so they all, IBM as well, had their own protocols. They all did it, but yeah, we've all gone to TCP/IP. So TCP/IP protocols operate at the application, transport, and internet layers. And so what they're saying is that these three top layers here are part of TCP/IP. This bottom layer, the network access layer, we certainly need it, but it's actually not part of TCP/IP. TCP/IP just uses it. It needs it, and uses it, but it's not part of it. And so, of course, Ethernet is not part of it. As long as IP can talk to Ethernet and vice versa, we're all good, basically. And so, again, we're back to that stack that we were looking at a little earlier with the web server and web browser. Now, a little more thorough, but again, application layer, there's a lot more than that. And so DNS is, of course, what we use for naming, host configuration, DHCP, for version 4 and version 6 of IP. There's also stateless auto configuration, email, SMTP, POP, and IMAP, FTP, SFTP, and TFTP. And there's also web, so HTTP, HTTPS, and REST. Now, as I said, when it comes to transport layer, there's two options: the industrial strength error checking one, or there's the quick and dirty one. Now, both have their advantages. If you start using voice over IP, you don't want TCP, you want UDP. But if you're trying to transfer files or web pages, you want all of that file or web page, and so that's when you use TCP. So when it comes to the internet layer, IPv4 and IPv6 are the major options. NAT, of course, is mostly used to as a bit of a patch for IPv4 because we're running out of addresses. ICMP, and so basically again for version 4 and version 6, and then there's neighbor discovery, which is a bit like ARP. And then routing protocols depending on what we're using. And so OSPF, EIGRP, BGP, RIP, among others. And now network access layer, Ethernet or wireless LANs are the most common use of that. ARP I'd normally put actually between that. And so it actually resolves layer 3 addresses into layer 2. So I sort of put it on the boundary between the two. But anyway. Now, so TCP/IP is an open standard protocol suite that is freely available to the public and can be used by any vendor. A standards-based protocol suite that is endorsed by the networking industry and approved by the standards organization to ensure interoperability. And so, everyone, I've got an Android phone that uses TCP/IP to get on the internet. I'm using a Windows workstation using the same protocol suite, implemented by different vendors. Okay, so the TCP/IP communication process. And so if a web server is going to send a web page to the client, it's going to pack it up into, it's a page. So, however big that page is, there it is. And so from there, it may well actually need to chop that page up into smaller chunks. And so, so that page may well be sent using multiple packets. And so that's what TCP does. It chops data into segments and then it numbers those segments so that the receiving end can then put them back together in the right order, because they may not necessarily arrive in the right order. So networks are rarely that simple, especially between a web server and a web client. And so basically from there, TCP has its header information. It identifies, what the source application was, so typically either port 80 or port 443, and of course the destination is whatever the client attached with, so that would be another port number. So it identifies which applications are on either end of this communication. It of course moves the data, and then IP of course addresses it, puts the source address of the web server, the destination address of the web client, and then of course to get it over an Ethernet cable, you actually need to have Ethernet header as well, and also a footer. So there's the error checking there, and then there's the addressing and other information in the front. And so that's the encapsulation process. And so encapsulation is when you surround the data with other stuff. De-encapsulation is when it arrives at the destination and then the information is then interpreted. So when it arrives, Ethernet will actually look at the addressing and also make sure there's been no errors and look at the addressing. Is that destined for me? Oh, yes, it is. All right. So then it'll pass it up to IP. Again, IP will confirm that the destination IP address is its IP address. And then from there, TCP, it's going to the web browser port. That's still active, is it? Yes. Okay, good. And so it will know who to give it to. Again, it will check for errors. And of course, it will wait for all of those segments to arrive so it can reassemble the data into that entire web page again. And then once it's finished with that, it will then send it to the browser and say, here's your page. Okay, so standards organizations. Now, there's quite a few of them involved in networking. They all sort of have their own specialities. And so there's open standards encourage interoperability, competition, and innovation. Standards organizations are vendor neutral, non-profit organizations and established to develop and promote the concept of open standards. Now, it says they're vendor neutral, but the vendors are normally parts of those standards organizations. And so, we're talking about Cisco. Well, they're members of the IETF. They actually Internet Engineering Task Force. And so they're deeply involved in that, and they either develop new protocols and get them approved, or they maybe work through what other people have proposed and, pass comment and maybe improvements. Now, some of those are the ISOC, which is the Internet Society, promotes the open development and evolution of the Internet. The IAB is the Internet Architecture Board, responsible for management and development of Internet standards. IETF is the Engineering Task Force, which I mentioned earlier, develops, updates, and maintains the Internet and TCP/IP technology. And there's also the IRTF. And so they're the Internet Research Task Force, focused on long-term research related to the Internet and TCP/IP protocols. And so basically, there's a bit of a structure there. And these are all just Internet standards. There are more standards bodies involved. Next page. Well, all right, next page after this. And so basically, standards organizations involved with the development and support of TCP/IP. So there's ICANN and also there's IANA. ICANN is the Internet Corporation for Assigned Names and Numbers. And so it coordinates IP address allocation, the management of domain names, and assignment of other information. IANA oversees and manages IP address allocation, domain name management, and protocol identifiers. And so ICANN is sort of the overall controller, while IANA is the let's get it done type of solution. And so so basically, the internet registries around the world actually go to IANA for their address space. They also, of course, manage different parts of the domain naming system, and of course port numbers can be assigned there as well. Now, other standards organisations, so the IEEE is the Institute of Electrical and Electronics Engineers, and so when you look at a LAN standard like Ethernet or wireless, they are actually managed by the IEEE. So any standard that starts with an 802, like 802.3, 802.11, they are managed by the IEEE. So there's the Electronic Industries Alliance, also often working very closely with the Telecommunications Industry Association. So often it's EIA, TIA, they often get together on these things. They develop standards relating to electrical wiring, connectors, and 19-inch racks used to mount networking equipment. And telecommunications look at things like radio, cell towers, VoIP, and satellite communications. And so the ITUT is the International Telecommunications Union Telecommunications Standardization Sector. So defines standards for video compression, internet protocol, TV, broadband communications such as DSL. All right, that's enough of those. Now, the layered models. So basically, these are how communications are organized. Now, we've already spoken a bit about the TCP/IP model, and so we have the application layer, transport, internet, and network access. Now, that's the TCP/IP model. That's been around for ages, and of course, that's what is implemented in the TCP/IP model. And we've already pretty much spoken about these, and these all pretty much belong to this side. Now, the OSI model was developed by the International Standards Organization, and this is the way that they deem to think things should be set up when it comes to communication. So starting at the top, when you're sending, application, presentation, session, transport, network, data link, and physical. Of course, when you receive it, it arrives in the physical layer, and of course you go in the opposite direction. So, so basically, they're organized a little differently, but you can see they're pretty consistent. And so basically, these are just design decisions that different people made differently. And so the network access layer takes up data link physical layer. That's because, as I said before, it's actually not part of TCP/IP, and so it's sort of, well, we need that to access a network, so that's what we'll call it. But really, it's the Ethernets and the wireless and or whatever it might be. While, layer 3, pretty consistent, layer 4, pretty consistent. They've just bundled application, presentation, and session together when it came to the TCP/IP model. Okay, so the benefits of using a layered model, there are benefits of using it which assist in protocol design, because protocols that operate at a specific layer have defined information they can act upon and define interface to the layers above and below. They foster competition, because products from different vendors can work together. They prevent technology or capability changes in one layer from affecting other layers above or below, and provide a common language to describe network functions and capabilities. And so basically, it's making it modular. So networking is a complex thing. If you try to do it in one piece of software, it'll be a nightmare. And basically, modifying it, so improving it would cause lots of hassles as well. So making it modular, different bit for each thing that they do. And so I suppose the best example of that is, we're going from IPv4 to IPv6. So basically, all you need to do is make sure you've got an interface with the layers above and below that is consistent. And, they've made the address 4 times longer in IPv6, but it can still talk to the transport layer, can still talk to the data link layer. All they had to do was give IPv6 a protocol number basically for each, for these two, and then that was it. That was all they needed to do, because each layer does its own job and then it passes it to the next layer. Passes it down if you're transmitting, or it passes it up when you're receiving. And they do their own job, and they don't worry about anything else. And so basically it's breaking that big problem in networking into a lot of small, easier to solve problems, and that's why they've done it that way. And yeah, so there was a problem with the IP version 4, not enough addresses, so they just had to fix that one little bit, not the entire system. And so that's the advantage of the modular approach. Now, 7 layers, not necessarily the easiest thing to remember. Application, presentation, session, transport, network, data link, and physical. There's a couple of tools you can use to help you remember. So basically the first letter from each of these, all people seem to need data processing. There's another one, an Australian flavoured one. Australia Post sucks, they never deliver parcels. Anyway, and so that's, I suppose, a little more humorous as well. And so basically each layer has its own job, as it says. So explaining the layers, and so the application layer is mostly about the interface between the network and the computer. And so be that a web browser, or maybe it's Word wanting to save to a network drive as opposed to a local drive, all of those kinds of things. Presentation layer is about how data is represented. And so, there's ASCII, there's Unicode, there's JPEG, there's GIF, there's, MP3, MP4, all of these kinds of data, they're all sort of represented there. And so basically the two ends need to agree on, well, what do we both support that's in common? That's basically what the presentation layer is about. So the session layer is about basically managing the data exchange between the two hosts. Transport layer is about, as we said, segmenting the big chunk of data into smaller segments, actually transferring the data, and then of course numbering those segments so they can be reassembled at the other end. Network layer is all about identifying the source and the destination, and of course routing those packets towards the destination. Now, from layer 3 and up, these sort of end-to-end, IP addressing is source and destination. Transport is reliably getting it from that source to the destination, and all the other ones are about the data and other things like that. Now, the data link layer and physical layer, of course, when I talk to the Cisco server, I'm in Adelaide, it's in, I'm assuming, San Jose, there's going to be more than one router involved, and so there's going to be more than one network. And so, of course, I'm sitting at home recording this at the moment, and so, there's my computer over Ethernet to the router, and then from the router, it's going over DSL to a node, which is then going on fiber, and then it's going to the exchange, and then my ISP, and then and so on and on and on and on. And so the data link layer is all about what link is it traveling over at this moment. And so Ethernet in my room, great, puts an Ethernet header on it, and my MAC address is the source address, the router's MAC address is the destination address, because that's where it needs to go to next. And so basically it's much the same as, if we were going to walk from, I don't know, the classroom to the coffee shop. Part of your brain has to think about the entire trip. So where am I? Where's the coffee shop? And what path am I going to take? And so that's the top layers. While the bottom half of the thing is, well, I've got to get out the door. I've got to walk certain steps. Step 1 foot in front of the other to get to the door, and then down the hallway, and then the lift or the stairs, and then across in what direction. And so you've got to. Part of you's got to be thinking about the full process, while the other one's got to be thinking about what bit am I doing at this moment. And so that's basically the bottom 2 layers are about the hop I'm doing at the moment, while the top 5 layers are about the entire trip. And so, yeah, there's so many analogies you can make for that. But anyway, okay. So TCP/IP, same process, but different steps but much the same job. So comparing, as I said, application layer incorporates the top 3 layers of the OSI models layers, and of course the network access layer, as I said before, is basically not their problem. TCP/IP, not really their problem. That's the IEEE or you know, ITUT basically worries about the bottom two layers. Okay, data encapsulation. So we have mentioned it before. So segmenting messages. Why do we chop big data units up into smaller ones? Well, basically it's because rarely do you have a network to yourself. So even at home, you know, you might have a computer plugged in using Ethernet, but there's probably someone else using their mobile phone, and maybe you've got a TV running that's using Netflix or whatever it might be. There's going to be multiple conversations going on. And so basically it's about sharing the resources that are available. If I was sending a 10 gig video file to somewhere and it went in one big chunk, no one else would be able to do anything. And so it's not very caring and sharing. And so that's why one of the reasons why they chop it up. Another one is basically efficiency, in that if I started sending that 10 gig video file and there was an error, I'd have to start again, wouldn't I? Because where is that error? And so by having the smaller chunks, you can actually do error checking on each small chunk, and so you don't have to resend the entire data stream if it fails. And so there are more than one reason why we do that. And so that's why TCP chops up the big data chunk into segments, numbers of segments, so of course it can be reassembled at the other end. But basically it's just so you can share bandwidth with others as well as recover from errors more efficiently. And so basically you sequence it so that when they arrive at the destination machine knows how to reassemble that message as it should be. Now, when we talk about encapsulation, one of the things we talk about is the protocol data units. Now, when it comes to the application layer, we normally talk about data. So we're moving data, be that a web page or an email or a video file that I was talking about earlier. Now, that's fine, but of course, TCP will chop it up into multiple segments, and then, of course, treat each individual segment separately. And so each individual segment will then get a transport layer header, which of course has source and destination port numbers and error checking and other such things like that, flow control, all within the header. That's great. Then it goes down to the IP layer or network layer. And of course, the network layer is all about source and destination addresses. So we'll put that in the IP header as well as some other information as well. And so that's the end-to-end information. That pretty much, this chunk will pretty much stay the same the entire trip. And then of course, it's got to go on the step along the way. And so the first step, let's assume it's Ethernet. And so you put an Ethernet header and trailer. So the header is all about source and destination addresses, protocol numbers, and other things like that, while the trailer is that error checking. And so that's the way that we get it across the hop that it's crossing at the moment. So then, of course, once data link layer has done its job, it then is the physical layer's job to actually encode that string of ones and zeros onto the medium. So we'll then, of course, get to the other end of that medium. And so when it comes to protocol data units, I've pretty much mentioned most of them, but maybe not all of them. So application layer, we always talk about data. Transport layer, segments. Network layer, it's always a packet. Data link layer, it's always a frame. And then for physical layer, it's the individual bits or a bit stream. And so some companies can be very wishy-washy, especially on the difference between a packet and a frame. Of course, that's not necessarily their home court that they're playing on, but so often things will be called a packet when they're actually not. But when it comes to Cisco, they will be very precise on their wording for data, segment, packets, frames, and bits. So you just got to remember that, especially when you start doing the chapter tests. Okay, so as we said, encapsulation is a top-down process. We have data, we then chop it into chunks, and then we start putting headers on it. So it's a top-down process. The level above does its process and then passes it down to the next level. This process is repeated by each layer until it is sent as a bit stream by the physical layer, the bottom layer. And of course, de-encapsulation is the reverse of that process. It arrives at the destination as a stream of ones and zeros, and so it needs to then receive that stream, and then once it's all arrived, it will then have a frame, and then layer 2 can decode that frame, and so is it destined for me? Okay, well, yes it is. All right, well then I'll pass it up to IP then, and then IP will then look at it and say, is it really destined for me? Okay, and then the segment will look at it and go, okay, this is segment X, and it's got no errors. Cool, I'll add that to my collection. Once all the segments have arrived, it will then be reassembled in order, and then it will be handed up to the application layer as that big chunk of data. Okay, data access. So basically, to be able to talk on a network, you normally need to have addresses. Now, there's often more than one address, and so especially when you're talking about LANs, local area networks, when there's possibly quite a few hosts, both data link and network layers use addressing to deliver data from source to destination. So the network layer source and destination addresses are responsible for delivering the IP packet from the original source to the final destination. And so, as I said, IP is end-to-end, while data link layer source and destination addresses, or MAC addresses, are responsible for delivering the data frame from one network interface card to the next. So that's always on the same network. Okay, so of course layer 3 addresses are logical addresses, and so when it comes to the IP header, it has a source IP address and a destination IP address, and so of course that's the source address is the host that created the packet, and the destination address is the one that's destined for. Now the destination may well be on the same network as it started, or it might be on a different network. And so in this case, it's a different network. It actually has to go through two router hops before it gets to the destination. Now, when it comes to IP addresses, the reason we bother is that they, be that IPv4 or IPv6, they each have a network portion and a host portion. And so that's how we route things across the internet, is that the internet routers don't need to know how to find every host on the internet. They just need to know how to find every network on the internet. Still a big job, but it's a less big job. And so basically, looking at these addresses, I'd assume that the source address means that this host belongs to network 192.168.1, and it's host number 110 on that network. While this web server probably belongs on network 172.16 and is host 199, and that will depend on the subnet mask, which we'll get into a bit later. And so there's always the network portion is always the first part of the address, and the host section is the second part of the address. And so every host on the same network will actually have the same network number. But of course, they need to have a unique host number so that they're uniquely identified. Now, when it comes to, and so we're looking at here is we've got PC1 talking to FTP server. They're both on the same network. And so when devices are on the same network, the source and destination will have the same number in the network portion. So it's 192.168.1 is the network number on both. The FTP server is host 9. The PC1 is host 110. Now, these two both have a MAC address, and so PC1's MAC address is all A's, a little fanciful, but anyway, and the destination MAC address is all C's. So that's the FTP server. Now, basically, we've got a bit of redundancy here because it's a local address. You probably could have just gotten away with the MAC addresses and all would have been good, but we're being consistent because we're using TCP/IP. And so this will work nicely, and they will be able to talk to one another. It's a little more complex when it comes to different networks. So when devices are on the same Ethernet network, the data link frame will use the actual MAC address of the destination NIC. MAC addresses are physically embedded into the NIC and are local addressing. The source MAC address will be that of the originator on the link. The destination MAC address will always be on the same link as the source, even if the ultimate destination is remote. Now, basically, MAC addresses, as it said, are actually physically embedded on the Ethernet NIC. Now, the way that happens is if you were to manufacture network cards, you would actually need to contact the IEEE and ask them for a code. You'd probably have to pay for it. And so that's the first half of the MAC address. Now, MAC address is 48 bits. And so the first 24 bits would be a unique code from the IEEE saying, all right, this is manufacturer John Smith. So that's your unique identification. So the following 24 bits just need to be unique on each device. And so 24 bits, 2 to the power of 24, how many is that? That's 16 million. So you can make 16 million NICs with that. So yeah, should be enough. And so basically that's the way the addresses work. Now, of course, there's no relationship between the MAC address and where they are on the planet. And so, they come out of a factory, Taiwan, China, something like that. And so one might come to Australia, the next one might go to Iceland, and the next one might go to Thailand or wherever it might be. And so there's no relationship between the MAC address and where it is on the planet. So if you were to use those to map where hosts are, you'd have to have an entry for every host on the planet. So that's a lot of hosts. And so a lot of information to keep track of. And that's why we use IP that has network numbers, and you just need to remember how to talk to certain networks. And so that's why we bother with the 2 addresses. Now, with a device on a remote network, what happens when the actual ultimate destination is not in the same LAN and is remote? What happens when PC1 tries to reach the web server? Does this impact the network and data link layers? Well, yes, it does a bit. And so as you can see from the IP header, the source address is still the same PC1. Destination is the web server, so it's a different network number. Now, hosts, it's not their job to know how to find other networks. All the host needs to do is look at this network number and this network number and go, they're different. So that's on a different network, that destination. So I need to use the router to talk to that host. And so when it encapsulates it, the destination MAC address will be for the router. Now, of course, when you tell your host how to find the gateway, it's the IP address. And so your host would need to actually do what's called ARP, or ARP, Address Resolution Protocol, and it will actually find out what the MAC address of the router is. And so when it forwards it, as it says the destination here. Of course, the switch will forward it and go look for that in its tables. Oh, okay, no, I know where that is. That's router 1. When it arrives at router 1, it will go, oh, that MAC address is mine. That's destined for me. So it will actually look at the packet and take notice. Then it will look at the destination IP address and go, oh, that's not really me. I need to forward this packet. And so then it will look up its routing table, and then it will start the process of aiming it towards the destination. And so the role of network layers addresses, when the source and destination of a different network portion, this means they are on different networks. And so pretty easy to pick there for us, at least. Computers are a little bit stupider though, I suppose. And so when the final destination is remote, layer 3 will provide the layer 2 address of the local interface of the gateway or the router. Default gateway is the router interface IP address that is part of this local LAN and will be the door or gateway to all other remote locations. All devices on the LAN must be told about the address of all their traffic will be confined to the LAN only. So if you don't tell a host its gateway address, you will not be able to talk to remote hosts. All right, once layer 2 on PC1 forwards to the default gateway, the router then can start the routing process of getting the information to the actual destination. And so the data link addressing is local addressing, so we'll have the source and destination for each link. And so, of course, the first hop that it does will have a source of all A's and a destination of all ones. While the layer 2 local addressing will change from link to link and hop to hop, the layer 3 address will stay the same. It's the layer 3 that actually gets it to its destination, all the way to its destination. The MAC addresses are each hop along the way. Okay, so data link addresses. Since data link addressing is local addressing, we'll have a source and destination for each segment or hop of the journey. And so basically the MAC addressing for the first segment is source PC1, destination the router, which of course is the first host that needs to receive that frame on the way. The MAC addressing for the second hop will be source will be the first router, destination will be the second router. And then the last hop, we've finally gotten to the same network as the web server, and so the MAC address, source address will be the router here, and the destination will be for the web server, finally. Notice that the packet is not modified, but the frame is changed. Therefore, the layer 3 IP addressing does not change from segment to segment like the layer 2 addressing does. So the layer 3 addressing remains the same since it is global and the ultimate destination is still the web server. Okay, so we've come to the end. So what did we talk about in this chapter? So the rules. So protocols have a sender and receiver. Common computer protocols include these requirements: message encoding, formatting, encapsulation, size, timing, and delivery options. Does depend on what the protocol is designed to do. Protocols to send a message across a network requires the use of several protocols. Each network protocol has its own function, format, and rules for communication. And so protocol suites are a group of interrelated protocols. So the most common one today is TCP/IP. Standards organizations encourage interoperability, competition, and innovation. Reference models, so the two major ones are TCP/IP and OSI. So TCP has 4 layers, OSI has 7 layers. Data encapsulation, so the form that a piece of data takes at any layer is called its protocol data unit. There are 5 of those, so starting out with data, then segment, then packet, then frame, then bits, going down the stack or encapsulating process. Data access is the network and data link layers are going to provide addressing to move data through the network. Layer 3 will provide IP addressing and layer 2 will provide MAC addressing. The way these layers handle addressing will depend on whether the source and destination are on the same network or if they're on different networks from the source. And there's the logo. So that's chapter 3 done. And so chapter 4, I think we start talking about the physical layer. So I'll talk to you again about that. I'll see you next time. Have a good one.